Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit number 6, Lesson number 4 on the midpoints of a triangle. Now this is going to seem like a rather odd diversion because we're in the middle of Unit 6, which is all about quadrilaterals, and really special quadrilaterals like trapezoids, parallelograms, rectangles, rhombuses, squares, etc. And yet today what we're going to do is kind of take a little bit of a diversion and see what happens when you connect the midpoints of two sides of a triangle with a line segment. So let's jump into that right now. All right. We're going to start off in the coordinate plane where we can really get a sense for midpoints, slopes, distances, things like that. And let's take a look at what exercise 1 asks us to do. In the diagram shown, triangle ABC is drawn with vertices at -3, 9, 9, 5, and -7, -7. Using the midpoint formula, find the midpoints of sides AB and AC, then plot and label them D and E respectively. All right, great. So, look, we've already gone through the midpoint formula many different times. Why don't you go ahead and find the midpoints of line AB and line AC, okay? Go ahead and pause the video now and take a few minutes. All right, let's go through it. Remember, the midpoint formula is just averaging the x-coordinates, averaging the y-coordinates. So for AB, the midpoint we'll find by doing -3 plus 9 divided by 2, and 9 plus 5 divided by 2. Okay, that's going to be 6 divided by 2. And 14 divided by 2, and that's going to give us a midpoint at 3, 7. All right, the midpoint of AC, let's do that. That's going to be -3 plus -7 divided by 2, 9 plus -7 divided by 2. That's going to give us -10 divided by 2, and let's see, 2 divided by 2. And that's going to give us a midpoint at -5, 1. All right, there we go. Let's get them plotted. Let's see, 3, 7 puts us right here, and that's point D. All right, -5, +1 puts us right here, and that's E. All right, so simple enough. Again, one of the nice things about actually plotting the two midpoints is it gives us a good check to see if these things are reasonable. If we had plotted these two things and they weren't even on those line segments, then they couldn't have been the midpoints of the line segments. But let's take a look at letter B. Letter B says draw in segment DE. All right, so let's do that together really quick, just kind of have it up there. Let's get segment DE drawn in. Okay, great. Collapse my ruler, throw it up there. So we've got DE drawn in, wonderful. It says then, using the distance and slope formulas, find the length and slope of both DE and of BC. All right, so I want the length of DE and the slope of DE, and I want the length of BC and the slope of BC. All right, what observations can you make about these two segments? So we're using the tools of coordinate geometry, the slope formula and the distance formula to find those lengths and those slopes. So let's take a look. Let's kind of go through them. All right, we've got the 2 points, but let me put them right here. What we need is we need point B, right? It's at 9, 5. We need point C, just so that we have them sitting right in front of us as we go through the work. We'll also need D. Would have been a little bit smarter to put that over here, but whatever. D is 3, 7, and E at -5, 1. Now I've actually got a little grid here with everything plotted, so we'll be able to see it very nicely. Let me do extending the page a little bit. Okay, so we want the length of DE, we want the slope of DE, the length of BC, and the slope of BC. Pause the video now and work through all 4 of those calculations, and then if there's an observation you can make, go ahead and do so. All right, now that should have taken you a while. It takes a little bit to just crank through all the numbers. So let's go through them. The length of DE, here we go, the distance formula. The square root, let's see, we're working with -5 minus 3 squared plus 1 minus 7 squared. All right, that'll be -8 squared plus -6 squared. That ends up being the square root of 100, which simplifies nicely, and that's 10. Let me do the slope of DE right away. The slope of DE is going to be 7 minus 1, all divided by 3 minus -5. That gives me a -6 in the numerator, +8 in the denominator, and I can reduce that to -3/4. All right, so the length of DE is 10 units. The slope of DE is -3/4. Let's go through BE. All right, for BE, or sorry, for BC, my apologies, the distance, right, is going to be -7 minus 9 squared plus -7 minus 5 squared. Lots of -7s in this. -7 minus 9 is -16 squared, -12 squared. And if you work out what all of those are squared added together, you'll get 400, or the square root of 400, and that will give me a length of BC of 20. All right, let me circle this so that we've got it. Let's do the slope of BC right away. The slope of BC will be -7 minus 5 divided by -7 minus 9. That's going to give me -12 in the numerator and -16 in the denominator. All right. Something went wrong here. 7 minus 1. Oh, silly, silly, silly. I knew something was going wrong here. 7 minus 1, for some inexplicable reason, I said was -6. It's not. It's obviously +6, which makes that slope +3/4. All right. So, -12 divided by -16 is a positive, and all of that will reduce down to 3/4. I knew that DE had a positive slope. I could see that it was going uphill, so that -3/4 was driving me nuts. For some reason, 7 minus 1, -6, who knows. All right, so let's take a look at this. DE has a length of 10, BC has a length of 20. DE has a slope of 3/4, BC has a slope of 3/4. So what two observations can we make about DE compared to BC? Well, one observation, obviously, is that DE is 1/2 the length of BC. Right? It's 1/2 the length of BC. It's 10, that one's 20. Likewise, though, we can say that DE is parallel to BC. So when I connected the midpoints of these two sides with a segment, I got a segment that was half the length of that one and was parallel to it. And it looks pretty parallel, right? Again, hard to prove at this point. And that's really the major conclusion from what we're doing today. First, before I move on, let me pause for a second. You can write down anything you need to. Hopefully get rid of any kind of negative you might have on the slope for 3/4. And then we'll move on. Okay, let's do it. All right, the midpoints of a triangle. When the midpoints of any two sides of a triangle are connected, the line segment created is parallel and half the length of the third side. Isn't that amazing? When the midpoints of any two sides of a triangle are connected, the line segment created is parallel to and half the length of the third side. Let's take a look at this on GeoGebra just a bit, right? Here I've got this nice generic triangle, okay? And what I see is that point D and point E are the midpoints of these two sides. I can move around any three of the vertices on this triangle, and what I'll always note is that this red segment will always be parallel to this one and half the length. Now I've got GeoGebra set so that it's rounding to the nearest tenth, so it may not always look like it's half the length, but DE is 5.9, AC is 11.8. Sorry, I can't get the numbers really nice for you. I almost had one. There we go. DE is 4, AC is 8. The parallelism is a little bit harder to see, of course, but we could always ask, let me just kind of pop off for just a second, and I'll draw a full line through DE, and then you're going to see the parallelism just a little bit better. So let me get that full line. What I'll do is I'll ask GeoGebra to draw a line between these two, and maybe a line between these two. And there, I think it's a lot more obvious. Now it's harder to see that half the length business, but here you can really kind of see that parallelism as I make those lines much larger. Okay, so we're now going to take it as a fact that when you connect the midpoints of any two sides with a segment, that segment is half the length of the third side and is parallel to it. We'll eventually prove that. It's going to be a really cool proof. I've been jazzed to do this proof for units and units now, okay? But that'll be the last thing that we do. Let's just kind of apply the theorem a little bit. It's very easy. Let's take a look at a kind of a standard problem along this lines. Exercise number 2 says, if a triangle with side lengths of 10, 14, and 18 has the midpoints of all three sides connected by segments, what must be the perimeter of the triangle formed? Draw a picture to help explain your work, or even to just help visualize your work, all right? So let's kind of talk about this. This is simple enough. I'm gonna draw just kind of a random sketch of a triangle, all right? I might even label it as ABC, okay? And what I was told is that one side length was 10, one side length was 14, and one side length was 18. If I actually took the midpoints of all three sides of these triangles, which are, you know, kind of like that, if I connected these two, what that theorem tells me is that it must be 9. It must be half of the 18. If I connect these two, it's got to be half of that 10. It's got to be 5. And if I connect these two, it's got to be half of the 14, or 7. And of course, you've been looking at perimeter since about 4th grade. The perimeter then of this triangle is simply 9 plus 5 plus 7, which, if I don't miss my mark, is 21. All right? So very easy, okay? But it obviously relies on that theorem, right? If I'm connecting these two midpoints, the side created must be half the length of this side. It's also got to be parallel to it, but for this particular problem, that's irrelevant. Likewise, I connect these two midpoints. That 5 needs to be half of that 10, etc. So a very easy problem. Anyway, pause the video if you need to now, and then we'll move on to another one. All right, let's keep going. So the last problem really had to do with that half the length. Let's see if we can do one that has something to do with that parallelism. Exercise number 3. Triangle LMN has vertices at 6, 11, 13, 7, and 2, 1. If the midpoints of sides LM and NM are connected with a segment, which of the following would be its slope? Now, there's a couple different ways of doing this, right? One way is not knowing that theorem at all. Just not knowing it all, right? And then what you could do is you could literally come up with the midpoint of side LM, come up with the midpoint of side NM. After you had both of those using the midpoint formula, you could then use the slope formula and get the answer. You can do that. There's nothing wrong with that. But if you think about this for a moment, if I draw out this triangle, L, M, N, right? And it says if I connect the midpoints of LM and NM, you know, what would be the slope of that line segment? Well, the slope of that line segment must be the same as the slope of this line segment, because they have to be parallel to each other. So although you could do this in sort of a brute force way, as I just mentioned, midpoint, then calculate the slope, you can actually do it much faster by just simply calculating the slope of Ln. So why don't you go ahead and do that? Calculate the slope of Ln. All right, let's go through it. So it's simple enough. If I calculate the slope of LM, right, y2 minus y1 divided by x2 minus x1, I'll get negative 10 in the numerator, negative 4 in the denominator. A negative divided by a negative is a positive, and 10 divided by 4 is the same as 5/2. Choice 1. Choice 1. And again, what's kind of cool is just like in the first exercise, if we had calculated the two midpoints and then found the slope between them, we would have certainly gotten 5/2. But it would have taken a lot longer and 3 different calculations. All right, let's keep moving. Okay. Now, again, the conclusions, the two conclusions of the triangle midpoint theorem are easy enough to both visualize and to actually use in applied problems like the two that we just did. The proof of the triangle midpoint theorem is beautiful. It's elegant. And it takes a lot of what we've been doing in this unit and in Unit 3, all right? So I encourage you, if you haven't gotten caught up to speed on, your CP/CTC triangle proofs, on what conditions make a parallelogram, and all of that, then this last problem, which is going to be the proof of the triangle midpoint theorem, is going to be kind of challenging unless you're kind of up to speed on all of those. I'm going to assume you are, okay? So let's kind of walk through this. It's rather lengthy, and there's even some construction work involved, so make sure you have a straight edge and a compass that's handy, and let's get right into it. Let's take a look. Exercise number 4. In the diagram shown, triangle ABC has the midpoints of sides AB and AC marked with points E and D as shown. Using only a compass and a straight edge, extend DE through E to point F such that DE is congruent to EF, leave all construction marks. So let's talk about this. Sometimes you're asked to extend a segment through a point by a certain amount, right? And what that really means is I'm just going to bring my straight edge down here. All right, I'm just going to kind of extend that farther than I probably need to, like that, okay? And I want to ensure now that I extend it somehow to point F, so point F is somewhere on here, such that DE and EF are the same length. And I'm not going to do it using a ruler. I'm going to do it using the classic construction tool, right, which is a compass. Think about how you could do that. How could you locate point F? All right, well, we use the compass for the same thing we always use the compass for, which is simply to mark off a length. So what I'm going to do is I'm going to extend my compass so that its radius has the length of DE. I'm going to make that mark, that arc. I'm going to then move it over to here, and I'm going to make the same arc. All right, fold it back up. I shouldn't need that compass anymore, and that is point F. All right, simple enough. Great. Letter B is also simple. It says draw in segment BF. So let's do that together. That's also pretty easy. All right, maybe, oops, just gonna make this thing a little bit shorter. And let's get our best friend in there. Oops, no, that's not it. Okay. There it is. There's segment BF. Great. Now, what I'm going to be doing is I'm going to be taking this diagram and I'm going to keep reproducing it. You're only going to have it at the top of your sheet, but we're going to keep being able to see this diagram as we move on. Now, keep in mind, we are going to start now doing a proof, but the proof kind of starts with all of this, and this is something we could have done with any of the sides. I could have easily found the midpoint of side BC and done the same thing. I could have connected it and then extended it so that this segment was the same length as this segment, all right? But keep in mind everything we know at this point, and let's keep moving. All right, so letter C. Here's that diagram with all the constructions done. Letter C says, give an argument, or it should say give an argument. It says given an argument, but let's just have give an argument for why triangle AED must be congruent to triangle BEF. So why is it that this triangle up here must be congruent to that one down there? I'd like you to think about that for a little bit. Why is triangle AED congruent to triangle BEF? All right, well, let's talk about it. One thing that we know is that point E is the midpoint of side AB. Because of that, we know that AE is congruent to EB. In fact, I'm going to just start to write that down. Okay, because E is the midpoint of AB, AE is congruent to BE. All right. What else do we know? Do we know any other side lengths of those two triangles are congruent? Remember, we're based on what we know, not just what we can see. Well, we also know that DE is congruent to EF. Now, why do we know that DE is congruent to EF? Well, we know that because that was the way we constructed EF, right? So I can now say that DE is congruent to EF, and that is literally by construction. I made it that way. All right, so I have a side equal to a side and a side equal to a side. That's not going to be enough, okay? It's not going to be enough. Wait a second. I also know that this angle is congruent to that angle because they're vertical angles. Okay, so I'm going to say as well, I always need those phrases for some reason, angle AED is congruent to angle FEB because vertical angles, I'll just say vertical angles are congruent. So, ooh, my red came back. So triangle AED is congruent to triangle BEF by side angle side. Right? Side equal to a side equal to a side, angle equal to an angle. Side, angle, side. Okay. Now again, we're trying to prove the fact that because D and E are the midpoints of AC and AB, DE must be half the length of BC and has to be parallel to it. So keep that in mind. And what we've now proved is that this triangle and this triangle are identical to each other. Okay, letter D. Explain why, based on the fact that triangle AED is congruent to triangle BEF, that BF must be parallel to AC. Why does this then lead to the fact that BF must be parallel to CD? Okay, so first things first, right? Somehow, based on the fact that this triangle is congruent to this one, I want to somehow explain why I would know that BF is congruent to AC. All right? Yeah, AC. Okay? Why is that? Well, to prove that two lines are parallel, almost always you first have to show that either a pair of alternate interior angles are the same or a pair of corresponding angles are the same. But, right, we know that these two triangles are identical, which means that angle 1 must be congruent to angle 2. All right, so because triangle AED is congruent to triangle BEF, angle 1 is congruent to angle 2 by CPCTC, right? Those are corresponding parts of congruent triangles, so they're congruent. But that means that BF must be parallel to AC because a pair of alternate, hey, red, interior angles are congruent. Oh, the greatest smartboard quirk going there. Alternate interior angles are congruent. right? They're the angles of the z. Now I'm going to like change to red on purpose, right? If I draw in the z, right, these two angles are congruent by CP, and because they're congruent, AC and BF must be parallel. Now that wasn't the end of the story, or the end of the question. The question then went on to say, well, why does knowing that this is parallel to this tell me that BF must be parallel to CD? Well, that's simple enough. CD is a part of AC, so CD is parallel to BF as well. Now, something's starting to feel familiar. I now know that this side and this side are parallel to each other. I know they're parallel to each other. Okay? So let's keep going. So right now, I know that CD and BF are parallel to each other. Why must BF and CD be the same length? Now notice I say, give a careful explanation based on what you know, not just what the picture looks like. So again, why does CD, again, let's go red. Why do CD and BF have to be of equal length? Okay? Based on what you know. I want you to think about this a bit. Well, here we go, right? We know AD is the same length as CD because D is the midpoint of AC. All right? So I know that this and this, AD and CD, are the same length because D is the midpoint. But we know AD, hello red, and BF, that was a big one, are the same length by CP, I just can't let that stay. Right? So I know that AD and BF are the same length because they're corresponding parts of congruent triangles. So, by substitution, CD and BF are the same length. Oh, wait a second, this is cool. Why is this cool? Because we now know that CD and BF are both parallel and the same length. CD and BF are parallel and they're the same length. All right, pan up just a little bit. Why can you now conclude that DFBC is a parallelogram? Why can we say that? I kind of just gave it away in the last problem. All right, we can say that DFBC is a parallelogram because it has a pair of sides that are both parallel and the same length. All right, so in other words, CD is the same length as BF and is parallel to BF. And in the last lesson, we learned that there were many different ways of proving something was a parallelogram. One of them was that any quadrilateral that had a pair of sides that was both parallel and the same length had to be a parallelogram. Okay? How does this conclusion, i.e. how does knowing that this thing is a parallelogram, then result in the two properties observed by connecting the segments, by connecting the midpoints with a segment, right? In this case, DE, right? Why is it that now, based on the fact that I know this is a parallelogram, I can now say that DE is half the length of BC, okay? And DE is parallel to BC. Well, let's take them one at a time. Let's do the half the length thing. DF is congruent to BC, or CB, but for some reason I'm going to say BC, because opposite sides are congruent in a parallelogram, but, right, DE, mystery red, DE is half the length of DF. So half the length of BC. Right? Isn't that kind of cool? Right? We know by construction that DE and EF are the same length, so that means DE must be half the length of DF. Because DFBC is a parallelogram, therefore we know that DF and BC are the same length, but DE is half the length then of BC. So there it gives me half the length property. The parallel property is even easier. All right, got plenty of room. 2, we know that DF is parallel to BC because opposite sides of a parallelogram are parallel. So DE must also be parallel to BC. Right? I mean, we know that DF is parallel to BC, and DE is just a part of DF, so DE must be parallel to BC as well. That was similar to the argument we made before when we knew that BF was parallel to AC, so BF must be parallel to CD because CD was just a part of that whole thing. Isn't that kind of cool? Right? And what's amazing about the proof is how many different pieces it all puts together, right? It puts together things like congruent triangles. It puts together constructions to create congruent triangles. Because of those congruent triangles, we can then prove that we've got a parallelogram. And because we've got that larger parallelogram, we can then prove that a part of that parallelogram is half the length of one of them and also parallel to the other side. All right, that concludes the proof of the midpoint theorem for triangles. Let's wrap this lesson up. Now again, would you ever have to reproduce that proof, let's say, on any kind of standardized exam? Probably not. You might have to reproduce it in your own classroom, depending on your teacher. You definitely need to know the conclusions of the midpoint theorem, which are that if you connect the midpoints of any two sides, the segment will be half the length of the third side and parallel to it. And also, obviously, you want to understand the thinking that goes into the proof, because there's so many important parts in it that we've seen in previous lessons. All right, we'll get back to some special quadrilaterals in the next lesson with rectangles. For now, I'd like to just thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.